So the AP class has already completed the protein folding lab, and the MI class will complete the protein folding lab soon, this week. MI, first thing you're going to do is, my hope is that you're going to do your bioethics. At least two of the classes, first and third, will do bioethics on Monday. One class will do the WebXam on, and that'll be ninth period. That's on Monday. AP Biology, you should have completed you will all have completed the protein folding lab and should be working on their take-home final and your take-home final. On Tuesday, ninth period will begin the protein folding lab, while the rest of the classes will do the WebXam. By Wednesday, all MI classes should be on the same page. For all classes, this video should be a review to help you identify important ideas and make sure you check your understanding of how all these forces and interactions work with one another. Now let's start with this idea of a fat molecule in adipose tissue. So, fat on a human body and a mammal is in cells, and this is a cell. This is the nucleus of the cell, and the main function of adipose or fat cell is to store fat for a few purposes. Fat is insulative, so it insulates us from the cold. Fat is mainly a storage of long-term energy. So in times of starvation, mammals can use stored fat, for fuel. Think of a hibernating bear or any hibernating animal. They feed on their fat reserves. Also think of a deer in winter. There's not a lot of food. The same with squirrels. Squirrels actually don't really hibernate. They go in I don't know what you would call it, but they do stay awake stay active during the winter months, and they depend on their stored nuts, but also on their fat tissue. So during winter months, mammals do lose body mass because they lose the fat reserves that they've stored all spring and summer and fall. And it's in these cells, in these tissues, where you have these fat droplets inside the cell. This is what they look like. Now, a fat molecule is made of 3 carbon, a little chain of 3 carbons, and attached to those 3 carbons are these hydrocarbon chains. The word hydrocarbon is a word that a lot of the upperclassmen know already, or should know, but I'm going to review it again. And hydrocarbon just means hydrogen and carbon. Hydrocarbon, exactly what it sounds like. A bunch of carbons in a chain, as represented here by these black spheres. They would be spheres, and then I know they look like triangles, but they're actually spheres. And the spheres of these hydrogen are sitting on the outside, and then at this carbon chain, this hydrogen and carbon, hydrocarbon. By the way, if you may have heard of hydrocarbon fuel, and hydrocarbon fuels as gasoline and diesel. These hydrocarbons are literally chains of carbon and hydrogen, long chains of carbon and hydrogen. Some have 8 carbons, some have 10 carbons, whatever. But the point is that they're all hydrogen and carbon in a long chain. This is the fat. This is what fat is. A long chain of carbon and hydrogen. This is non-polar. Non-polar. We've gone over the difference between polar and non-polar. This is non-polar. So this will not mix. It will not go into solution with water. It won't mix with anything that's polar, like dissolves like. So these chains of hydrocarbons are stuck to this 3-carbon molecule here, and we'll look at it more closely in a little bit. Now, there's 3 different kinds. When you're talking about biomolecules, there's 3 different kinds of what we call isomers. In other words, they're similar. They're very similar. And a structural isomer, if you look at it, these 2 molecules, pentane and methylbutane, they're both hydrocarbons. They both have just carbon and hydrogen. They both have the same number of carbon and hydrogen. If you couldn't look at them and you just measured their mass, they would have the same mass because they have the same amount of carbon and hydrogen. Now, structural isomers just differ in just how you arrange the bonds. Because carbon has so many different ways of connecting them, in ring structures, in straight chains, in branched chains, you can connect these atoms in different ways with the same number of carbon and hydrogen. Because of that, they're different molecules, but they have the same number of carbon and hydrogen, so we call them structural isomers. Now, you've heard of trans fat, or at least I hope you've heard of trans fat, because it's horrible for you and you need to try to avoid it. It's found in McDonald's food often, or at least it used to be. I'm not sure, you'll have to look that up, but it was a real problem with anything fried, even baked stuff with margarine instead of butter. Produces these things called trans molecules, trans fats. And what's the difference between trans and not trans? All right. Well, in this case, and I know there's a lot of political and, sociological terms that are getting thrown around, but you've probably heard of trans and cis, but in this case, cis means they're on this, they're the same, they're on the same side. If you look across a double bond, if you just look at where the double bond is, there's a double bond here and there's a double bond there. You'll notice that in cis, they're attached to the double bond on the same side. So they're cis. All right. When you're dealing with a trans molecule, then the not carbon and hydrogen, right? The things that are not carbon and hydrogen that are hanging around the double bond. And what could they be? In this case, the X represents not an element. It's not xenon. By the way, xenon is Xe. There is no element X. X is a variable, okay? And this variable represents any number of things that could be attached here. Could be another hydrogen. Well, it can't be another hydrogen because then you wouldn't be able to tell the difference between these two. But it would be, an hydroxide group, and maybe over here you have, something else. But whatever's attached here, they're on the same side. Here, they're on opposite sides. Now, this actually becomes very important because shape is probably one of the biggest things that we have to worry about when we're talking about biomolecules. Biomolecules, their function, what they do in your body, a lot of it is determined by shape. The shape of the molecule determines a lot about its function. Structure, which we're going to go ahead and say shape, equates to structure in many ways, is informed by and is determined by, and in many ways the opposite is true, that function is determined by, is informed by structure. So these two, structure and function, depend on each other. The example I use in class often is, what do you call a window made of bricks that doesn't open. You call it a wall. It's not a window. So for it to be a window, it has to be see-through, and usually it doesn't have to open, but it has to be see-through. If it's a door, it has to open. So it has to have hinges that allow it to swing open. It could open up, it could be round, it could be rectangular, it could be round like a Hobbit door, but whatever, it has to swing open for it to be a door. So the same principle is going to be used when you're looking at cellular structure, at things that happen inside the body, when it comes to disease, when it comes to how things work. If its structure is going to inform and help determine its function. If you change the structure, you change the shape, you've changed the function. So the fact that these same elements in this example, because they're X, if you please notice that all of these are X, 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 and over here on this molecule, they're X, X. The only difference between these two molecules is the X's are on opposite sides. This one's up, this one's down. These two are both up. So because of that, this molecule is very, very different. They're very different. Now, so what, you might ask? So let's go ahead and write that. So what? So what? Why is that important? Well, the reason that's important, and just to be clear, is that this molecule, this trans molecule, won't function the way the cis isomer would. So in the case of trans fat, instead of the fat going into the cell the way it normally would and end up either being used, burned, or put into adipose tissue to be put away for later, what happens to that trans fat is it stimulates the production of these. If you look at, let's take a look at a blood vessel. If you look at a blood vessel, the trans fat encourages the production of these plaques. In this case, they're not bacterial plaques, they're buildup of these hard, brittle material that layers in the blood vessel and closes up the blood vessel so that the blood cells find it difficult to get through. And so what that leads to, as you close off, like putting your finger over the tip of a garden hose, you have an increase in blood pressure, and you also have the opportunity for material to get stuck there because the opening is smaller, and you have an increased risk of a blood clot. Blood clot is just something that dams up the flow of blood. It stops the flow of blood. Now, if that blood clot happens in the brain, we call it a stroke. Because that's going to kill whatever's down here, whatever cells are over here, whatever tissue, it's called tissue, is over here, is not going to get any blood. Those cells are going to die. And that's what happens to someone with a stroke. The cells die on the other side of the blood clot. If the blood clot happens and by the way, remember, brain tissue does not replenish itself. It doesn't go through healing. It's very difficult to heal brain cells. They don't reproduce. They can't make any more brain cells after a certain point in your development. Turns out that there's exceptions to that, but for the most part, that's true. So it's very difficult to replace that function once you lose that function. If that blood clot happens in your spine, you're paralyzed because those nerve cells die. If the blood clot happens in your heart, it's called a heart attack, right? It's a specific name for it, but we'll just call it a heart attack. If it happens in your lungs, you call it an embolism, a pulmonary embolism. Happens in, and by the way, just to be very clear, very much like a lot of the tissues specifically, there's two main things, main types of cells that there's a few more that won't repair themselves, that you can't make any more of. That's heart or muscle tissue, muscle cells. They don't go through the cell cycle. They will not replenish themselves. They won't repair. Muscle cells will not go through the cell cycle. So if you kill a muscle cell, you can't replace it. Now, that's not to say if you don't rip muscle fibers, that's a little different. You can repair the muscle fiber, but you can't replace the cell. So once they die because of a blood clot or whatever, the reason is it's over. That muscle's not regrowing. Brain tissue is the same restriction. You can't replace dead brain cells, nerve cells of any kind. You can't replace those cells, all right? So those neurons or those muscle cells, once they're dead, they're dead. So this small change of where that other group is, cis versus trans, can mean the difference between you having high blood pressure, a stroke, being paralyzed, having a heart attack, having pulmonary embolisms, permanently losing muscle and brain cells, between that and that not happening. So it's important that you identify what foods have these trans fats, and we can talk about what those fats look like at some later date. But the bottom line is, avoiding those trans fats make your prognosis of living a longer, healthier life, specifically healthier, so you're not dealing with a lot of the issues that a lot of us that are older have to deal with: high blood pressure, stroke, etc. You can avoid a lot of this by trying to avoid those trans fats. Another really good example of the difference between trans and cis isomer, and I'm going to leave it up to you to go look it up if you'd like, is this drug called thalidomide. Thalidomide was used in the 50s to help ladies that were pregnant deal with morning sickness, and it worked. The problem was that one form, they were two isomers. One isomer meaning they're made of the same atoms, right? But same atoms, but they're arranged differently. They're organized differently. They're connected differently. Well, we just looked at cis and trans. This next one's called an enantiomer. An enantiomer is even more subtle than the cis and the trans. The enantiomer, you have some central carbon. Notice that everything else is the same. All the there's NH2, there's an NH2, there's CO2H, there's CO2H, there's H, there's CH3, there's CH3, there's H. But because these two are on the left, because this arrangement is one way and this arrangement is the other, they call one of them left and the other one right. So because these two H's are on the right, they call this a right version or D isomer. And this one, because the H's are over here, they call it an L isomer. Like your right and left hand, they look very similar. If you look at your right and left hand, you can see that they're almost identical. But they have the same number of fingers, unless you lost one or you were born without one or something. But in general, people have the same number of fingers, same parts to it, same bones on both hands. But one is arranged differently, so one's right-handed and the other one's left-handed. So one's, in this case, these molecules will one be right-handed and the other left-handed. This is D isomer, this is L isomer. It turns out that the difference between these enantiomers, when we sorry about that, and I hate when I misspell, and I do it all the time. These enantiomers, the difference between them led to babies being born with serious birth defects. For one, and for the other enantiomer, no problems. And what was really interesting is that even if they made a bottle of the safe enantiomer, by itself, the molecule would flip. This thalidomide would flip and turn, half of it would turn to the other enantiomer. So if you had 100% of the L form, the L isomer, in the beginning, after given a certain amount of time, you would end up having if you had 100% of the L isomer, you'd end up having 50% of that original substance that you created. 50% of it would turn into the D isomer, would turn into the right-handed isomer. That seems like it's insane that it would just happen all by itself, naturally, no issue. I mean, no one changing it, no special conditions, kept in the same conditions in a very short period of time. They just simply could not make a safe version of this material. It just was a sad truth that you'd have to have 50% of the. You'd end up with 50% of the stuff that doesn't cause a problem, and then 50% of the stuff that does, and there's nothing you can do about it. That really kind of sucked, because that meant that no matter what you did, this material would end up causing birth defects. So 100% of the people that or most of the people that were given this drug for morning sickness, 50% L isomer and 50% D isomer. So this thalidomide was a real example of why it matters to answer the so what. That these different forms of molecules become very important. You have the example of trans fats being an issue. You have the example of enantiomers being an issue, the right versus left-handed molecule. And structural isomers also, I would hope it's obvious now that they're very different. In fact, when you look at fructose and glucose, and we'll look at it again in a bit, you look at fructose and glucose. They are structural isomers. When we look at fructose and glucose, you'll see that fructose and glucose have the same number of carbons. They both have 6 carbons. They both have the general formula. If we looked at carbon to hydrogen to oxygen, they have the same ratio. They have, for every 1 carbon, you have 2 hydrogens and 1 oxygen. So if you use this ratio formula for a carbohydrate, and that's what this is, in carbohydrates you expect to have 1 to 2 to 1. If you take a look at that, and you say there's 6 carbons here, remember the carbons don't always show when you're drawing these line diagrams. They usually they show the very minimum, right? So here's carbon, 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons. I'd expect to see 12 hydrogens, so let's count them. There's 2 here. This 2 means there's 2 hydrogens. If you don't see a number, it's 1. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 hydrogens. How many oxygens do I expect? 1 for every 1 carbon. So 6 carbons. So that means 6 oxygens. So 1, 2, 3, 4, 5, 6. So that works out for fructose, and the same will work out here for glucose. So they have the same number of atoms, same kind of atoms, they're just arranged differently. The double bond here is at the end, the double bond here is in the middle, somewhere in the middle. It's actually in the second carbon. Just rearranged some of the bonds. The sharing of electrons just are slightly different. So there's glucose, and when the ring closes, because of where the double bond is, this glucose turns out to be 6-sided. We draw it like a hexagon. So anytime you see a hexagon, usually with an oxygen here in the middle, often it's not the only hexose, it's not the only 6-sided carbohydrate, but it's the most important one that we're going to deal with. We call it glucose. So you see a 6-sided. Anytime you see a little this symbol here, they're generally talking to you about glucose. It's a sugar, specifically glucose. This one, 6-sided. But notice that when we count them, there's a 1, carbon 1. I'm just going to start at the 0. If this is oxygen, it's an O, not a 0, but let's imagine it's an O. It's a 0. There's a second carbon. Remember that where the 2 lines meet is a carbon. 3, 4, 5, 6 is sticking up. The 6 prime, by the way, that we number these prime to symbolize their order in the ring. So 1 through 6, you'll notice that 1 is sticking over here, and you can see that the one over here, it's that first carbon here ends up here on the right in glucose, and there's 6 prime sticking up. Now, if we take a look at fructose, because the double bond is here in the middle, you got this carbon, number 1, is actually sticking down there. 2 is this, so this is actually 1 prime. So you can imagine this oxygen, this double bond oxygen, is the reactive agent here that's making this ring. So the first prime is sitting out there. Second prime is there. Then third prime, fourth, 4 prime, 5 prime, and 6 prime. So you still have your 6 primes. It's just that 1 prime is sticking down, while here in the glucose molecule, You have in the glucose molecules, one is part of the ring. Here, one is not part of the ring because it's sticking out, just like it's sticking out here, it ends up sticking out in the fructose molecule. Okay, so here's that question again. So what? Who cares? Well, it turns out that glucose, you can digest glucose pretty well. It's really easy for you to deal with glucose. Your body deals with it really well. When you have too much of it, you produce insulin, gets it out of your body. Your liver can put it in cells, take it out of cells. I mean, your body does a lot of it. Can convert it. It easily converts it to this, to that, and the other thing. Your glucose is just really well handled by your body. Fructose, however, is a problem for your liver. If you eat too much fructose, you take in too much fructose, that could be a real problem for your liver. And again, if you lose your liver, that's a mortal issue. You're talking about that's part of the problem for alcoholics. They lose their liver in cirrhosis, and that's an issue. That should be a warning sign when you read high fructose corn syrup. In your drinks, and where you're going to get these. These are very high. This is corn taken from the cornfields all over the country, processed in a factory, and they produce a really concentrated form of fructose. So there's a lot of fructose in this corn syrup, and that's a real issue. That's a real problem for our bodies to digest, and it causes liver. It can cause liver damage. It can cause all kinds of issues metabolically with your being able to deal with that concentration of fructose in your body. So when you're drinking those sugary drinks, and please pay attention to the labels. They're not all sodas. Everybody likes to say that it's the soda that's the issue. Yes, soda is a problem, but it's not just sodas. You can look at your juices. They'll call themselves juices when really they're not. They're just drinks. So not all juices are squeezed fruits. And by the way, that's where fructose comes from fruit. The word fructose comes as sugar that fruits make. That plants put in fruit. So it's important that you understand that isomers in all their forms have a real impact on the function. One form is healthy under all things in moderation, is the old saying. So if you do, even too much glucose can be a poison. Too much water can be a problem. But the bottom line is glucose, right, can be tolerated well, which means you can take higher doses of glucose and still be okay. Too much still could lead to diabetes and other issues. But fructose can lead to there's less of it. You can tolerate less fructose only because of the shape of the two molecules. When we look at the enantiomers, the ones that are either right or left-handed, enantiomers are either right or left-handed. Let me rewrite that. Enantiomer, right? Enantiomers are either right or left-handed. They could lead to issues. In the example that I told you could go look up, and I think you'd be very interested to go look it up and seek the history on that. If you do, you'll on the internet, just a cursory search on the internet, you can find some real sad but really impactful, I hope, stories of how thalidomide impacted real people. And the sad name they gave a lot of these kids is flipper babies. babies being born with either no limbs or limbs that resemble flippers. It's a horrible name. I don't even like to, but you'll read about it if you look at the history. So I'm even going to just erase it. I don't even want to put it up, but I just wanted you to know that that's why they called him that. It's a horrible name to give another human being, but that happened because their pregnant mother trusted the medicine, and that medicine, unbeknownst to anyone, no one knew this was going to happen. They had no idea that this was going to happen. This is before the federal government did a lot of the required testing for drugs. So this is before the federal government even tested on, had any major tests on, required tests on animals and double-blind studies. None of that was done. So a lot of people were impacted before they could stop the use of this drug, thalidomide. So, and then of course you have the cis and trans isomers, right? The geometric isomers, cis or trans. And the example there is the cis and trans fat, and the difference and its impact on on the formation of plaques in your arteries and veins that can cause high blood pressure, high risk of blood clots, strokes, paralyzation, heart attacks, pulmonary embolisms, all that because of the shape of these molecules. All right.